All right, Algebra 2. Here's our lesson on rational function graphs and their asymptotes. So, we haven't talked about rational functions all year, except for the very first unit when we were talking about what parent functions were. Rational functions are equations that are y equals 1 divided by x, because if we're looking at rational functions, it's a ratio, and a ratio is a fraction. So that means when we do have an x as in the denominator, that actually means that we're going to end up having a rational function. And now there's going to be some special things, and we're going to talk about what makes a rational function unique. But for parameter changes, it's going to follow the same line as all of the other parameter changes for the functions that we've talked about. So that means it's going to be y equals a divided by x minus h. Now, I would encourage you to put parentheses with your denominator, because remember we talk about left and right being opposite of what you think because of the parentheses. Just kind of keep that in mind. And then if you do have a constant, that would be k. That would shift the function up or down. So that would be up or down. And then this one is going to be left and right. This h. Okay, and then a really represents your scale. Whether it's going to be horizontally stretched or horizontally squished. That's not the right word, but I can't think of the right word right now. Compressed. There we go. All right, so let's go ahead and take a look at this function. When it's just the parent function, y equals 1 divided by x, they already have a table here. So what I'm going to do is I'm going to go ahead and insert wherever I see x, I'm now going to insert that with the values on this table. So the first one is going to start off as y equals 1 divided by negative 2.5. And there again, I'm using this formula right here, and I'm just substituting wherever I have x is now these x values on this side. All right. So now I went ahead and calculated all of these. Where I'm doing this is just take your calculator. Come out, and there we go. So let's go ahead and we're going to take 1 and divide it by negative. Oh, hello. Ah, there it is. It was on the bar. Negative 2.5. Try that again. Okay. Negative 2.5. And that would end up giving us negative 0.04. So that's going to be our first value here. Okay. Now I went ahead and calculated all of these. You'll have to do that on your own for the others. Okay. So when we're looking at 2, it would be 1 divided by negative 2, which would just be negative 1/2. Okay, and then keep going down the line. So 1 divided by negative 1.5 is going to give you negative 0.66 repeating. I'm going to round it to 667. Now 1 divided by negative 1, that just gives me negative 1. And then 1 divided by negative 0.5, that's negative 2. 1 divided by 0. Now, if you were to type 1 divided by 0 into your calculator, you're going to end up getting an error message or undefined. Let's go ahead and see what this calculator says. Okay, 1 divided by 0. Cannot divide by 0. It just specifies that you can't do it. Okay, mathematically, this is like the big black hole. You can't divide by 0, because if you have something and you have to divide it amongst 0 friends, it wouldn't be able to go anywhere. So this is actually going to be undefined. And when we get to the graph, I'm going to show you what that looks like, because it does change your graph completely. All right, so let's go ahead and take a look at the next one. Is just going to end up being 1 divided by 0.5, which is 2. 1 divided by 1, which is 1. And you'll notice that the pattern is starting to repeat itself, kind of like a quadratic, but this is not a quadratic equation. Okay, so this is going to be 0.667. Positive 1/2, and our last one is negative 0.4. All right, next we're going to go ahead and graph these points on our graph. I went ahead and put some points on our graph. Negative 1, negative 2, negative 3, and we're going to go ahead and plot these points. So starting with negative 2.5 and negative 0.4, we're going to go over here, negative 2.5, and then negative 0.4, which is going to be down in the third quadrant. Next one is going to be negative 2 down to negative 0.5, negative 1.5 right in the middle there. Okay, this one's going to be negative 1, negative 1, negative a half, and all the way to negative 2, and it's going to start curving down. So here's our first graph, and I'm totally missing all of those points. Let's try that again. Whee! Alright, that one's much better. Okay, and it's going to continue on from negative infinity to negative infinity here as well as it approaches the range. Okay, but as I go closer and closer to 0, notice how our points change completely. Now we're over here. It's going to start at 0.5 all the way to positive 2. And then over here we end up with 1, 1. Next point is 1.5. So 0.6, so it's right here. And then 2.5 and 2.5 to negative, whoop, that should be positive, sorry, positive 0.4. Okay, so this graph is going to do the same thing, and in fact it's mirroring the other side alongside this y equals negative x, but that's a whole nother thing. Okay, so what's really happening at x equals, let's try the red. So what's really happening on the y-axis and the x-axis are, at this point, x equals 0, we have a vertical asymptote. This is where we will never have any values, and the reason being is because x cannot be 0. Okay, so x cannot be 0 in our solution set. All right. Now, we also have a horizontal asymptote, an HA. This would be a VA, vertical asymptote. And our horizontal asymptote is actually following along the y-axis because we do have the same issue. Okay, so as we approach positive to negative infinity, we will not have any values where y will equal 0. It just is not going to happen. So those are our vertical and horizontal asymptotes. Okay, and we're going to go ahead and talk about a few things. I'm going to scroll up and down from time to time, but let's go ahead and take a look at this. So what is the difference about this function in comparison to other functions we have studied this year? Linear, quadratic, square root, exponential, logarithmic. This is when I would ask you questions, but I don't get that privilege to hear you guys answer. So first of all, it would be two different graphs. Okay. And the fact that there are actually two asymptotes. Now, some of our graphs have an asymptote, so if like exponential or logarithmic, those have asymptote or one asymptote, but in this case we have two. And it's the only graph that has two asymptotes. All right, and of course all the others have one equation, but we can say that it's equation. So is the graph continuous? Okay, so when we're looking at this graph, we're looking to see that it continues from negative infinity all the way to positive infinity and doesn't break up. And the fact of the matter is, it does break up, and it's right there at the vertical asymptote. So we would have to say, no, this is not continuous. And we would say that because there are two graphs, or two parts. All right, so now it's asking what is the x-intercept. So when we have the x-intercept, that's where it crosses the x-axis, and in this particular graph, it doesn't do that. So we would have to say none. Now, what about the y-intercept? Okay, looking at the graph, it doesn't cross the y-axis, so we would say none here as well. For what x value is the equation undefined? And when we say set the denominator equal to 0, that would give us an undefined equation. In this case, it's when x equals 0. Later on, it's going to be when different, it's going to be different, and it might be a little bit harder, but you're just going to set the denominator equal to 0. So when we're looking for the domain is all x values, we would start from negative infinity, and I'm going to change colors here. So we would start from negative infinity all the way positive infinity, and look, we can't have anything on the vertical asymptote, and continue on all the way to positive infinity. So when I state that, for the purpose of this lesson, I don't want you guys going deep into the different forms of labeling domain and range. It's good practice, but I just want you to be able to understand that it's all real numbers except for when x is 0, because when x is 0, that's where our asymptote is, and it can't cross that asymptote. All right. Now, what is the range of this function? Same answer. It's going to be all real numbers all the way except y cannot equal 0. Okay, so an asymptote is a line that the graph approaches but never actually touches. So it'll get close, 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 but it'll never touch. Asymptote should be drawn on the graph with dotted lines. How many asymptotes does this function have? 2. Okay, give an equation of each asymptote. Whoops, this should have been give the equation for each asymptote. I don't think that should have been there. Oh, duh. I'm sorry, I read that wrong. So the asymptote we're looking at, we already wrote them here. This would be just x equals 0 in our horizontal asymptote. So our vertical asymptote, the one that goes up and down, would just be x equals 0. And the way you can really figure that out is this vertical asymptote. You would see what the x value is. And it's always opposite. People think, okay, wow, it's on the y-axis, it has to be y equals. But in this case, if we were to plot all of these points, it would start off as 0, 1, 0, 2. Now notice how all of these points have in common is that x equals 0. And that's what we're graphing. We're graphing the line that shows that asymptote, which would really just be x equals 0 for the vertical asymptote. Now the horizontal asymptote is going to be y equals 0 for the same reason. Okay, so now we're going to go ahead and move on to parameter changes with our rational functions. When we do that, remember, it's always best to go ahead and put the denominator in parentheses so that it reminds you of what's happening. And I'm going to go ahead and zoom this in so we can see. All right. Yeah, it doesn't like that. Let's try this. Okay, well, I have to leave it zoomed out. So the denominator is going to tell us basically where our vertical asymptote is. We just need to set it equal to 0. Okay, so in order to find the vertical asymptote, set denominator equal to 0. All right, so that's going to make sure we have vertical asymptote equal is, hey, go away. No. Is x plus 6 equals 0. I want to erase that other equal sign. It's getting confusing. Okay, so that means x cannot equal negative 6. So that means at negative 6, I have a vertical asymptote. So it's going to be 1, 2, 3, 4, 5, 6. Let's make that a little bigger. Okay, which makes sense because we talked about the denominator also changing it left, or changing the parameters left and right, and this is going to be opposite, so it's going to shift the entire equation left 6. Now our horizontal asymptote is going to be affected by our constant, which shifts up and down. In this case, it didn't shift up or down, so our horizontal asymptote is really 0. So it's going to end up just being y equals 0, and our vertical asymptote equals x equals negative 6. And we can write that down here. Should go ahead and make this smaller. There we go. So y equals negative 6, and whoops, that should be x. And y equals 0. Alright, So this graph is going to look just like this one, except for the fact that we picked everything up and moved it over. We're going to have to start with another video. So this will pick up from video.